Whoops. All right, we're ready to rock and roll. So we just got done taking a math test, right? All those equations about describing the movement or the energy of different particles or waves. And we realized at the very end that Bohr's model of the atom was incomplete. It's a good model, and that's probably the model that you guys were taught in middle school. The nucleus is in the center. The electrons go around the nucleus like the planets do. That's not completely right, okay? And the reason why it's not completely right is because the electron is both a wave and a particle. It has both natures. So the particle must then exhibit properties of both waves and particles, okay? So just to review our summary here, classical mechanics or Newton's laws, they work great for large objects like planets and satellites and spaceships, cannonballs, baseballs, whatever. Slow speeds, and when I mean slow, I mean slower than the speed of light. So 1,000 miles an hour, believe it or not, is slow. And because of those things, classical mechanics is exact or determinate. Okay? I can tell you exactly where a baseball will land. I can tell you exactly how long it will take. I can tell you exactly how long it will take a penny to fall off the Empire State Building and with what force it will hit the ground. But with quantum mechanics, that applies to small objects, things moving at very fast speeds, so we're talking close to the speed of light. And what ends up happening is we can no longer talk in certainties, we can only talk in terms of probabilities. Okay? So the last model of the atom, and the correct model of the atom, is called the electron cloud model of the atom, developed by Schrodinger in 1926. It's a mathematical model. And that's why we don't teach it to you, because it requires you to know calculus. Now, and not just simple calculus, complex calculus. Now, none of you have had calculus. And so what we're going to do is kind of give you a friendly description of what it is. But you really can't learn this model until you've had calculus. And even then, it's pretty difficult to understand more. Why do we teach it to you? Because it is the correct model of the atom. And it is the basis for understanding everything about the periodic table. It explains everything we learned first semester. Why does sodium have a +1 charge? Why does sodium want to bond with chlorine? Why is fluorine diatomic? It explains everything. So, before we talk about the model, we need to learn a little bit, or just review a little bit of our mathematics. Okay? So, let's learn some math, or review some math. If we were going to draw the sine wave, sine wave goes from what to what? 1 to -1, right? And where does the sine wave start? At 1 or -1 or 0? It's too early in the morning for your brains, isn't it? Sine wave starts at 0. Now it'll make it a little bit easier for you. Where does the sine wave equal 0? At 0, pi, 2 pi, right? And then it goes on, 3 pi. Is that a vague recollection for you guys? Now in math, what you just drew was the y equals sine x. Instead of using the variable y, we use the variable psi. Psi is y, and y is psi. So we would say psi equals sine x instead of that little pitchfork. Now what if we square psi? If you square psi, you're squaring this function. The amplitude is 0 at 0, pi, and 2 pi. Where is the amplitude the greatest? At pi over 2 and 3/2 pi, right? That's where the amplitude is greatest, half pi over 2, 3/2 pi. The only kind of problem with this is that here we have a negative amplitude because it's below the x-axis. So if you have a negative amplitude, it's not as good to talk about. So how could we change all of our negative values to positive values? Square. Right? That's what squaring does. Squaring takes all negative values and makes them all positive. Negative 2 squared gives you positive 4. So what this graph will look like, it'll look exactly the same, except now all negative values have become positive. So that's still pi, 2 pi, 3 pi, and the amplitude is still 1. So the purpose of squaring it, and this is the take-home message, Sarah, if you forget everything else, the purpose of squaring it is just to make all the values positive, so we don't have to deal with negative numbers. That's the purpose. All right, let's see if you can do this yourself, but do it backwards. Let's say I've got psi squared, and it looks like this. And the amplitude is 4. I got rid of the pi's because it's just harder. So I've got 10, 20, 30, 40. Here's my psi squared wave. The amplitude is 4. Could you draw me just psi? So in other words, you're going to have to take the square root of this. So just go ahead and try it. See if you can draw me what, this is psi squared, what psi would look like. Then write down the units, how big the amplitude would be. Squaring it affects the amplitude. Because what did squaring do here? It turned negative 1 into positive 1.
Yeah, but it doesn't like change the number. So it's
Well,
like
if I square,
what's 1 squared?
1 squared is 1. So
Thanks, Karen.
So first of all of you got this part right, that the negative amplitude would come back. Doesn't change these values, 10, 20, 30, 40. But the amplitude would be 2 and negative 2. Because if you square negative 2, what does it become? 4. So if you square 2, it becomes 4. If you square negative 2, it becomes 4. So there was a nice little lesson on sine wave. Okay, next math lesson. And again, the thing here to remember, Mulkey, is why are we squaring it? To get rid of the negative numbers. Okay, math lesson 2. We got a simple equation here, y equals x. If y equals 4, how many solutions, Tyler? Or I'm sorry, Jared, I meant Jared. If y equals 4, how many solutions are there for x? Y equals x. 4. How many solutions? It's early in the morning. 1 solution. I just want to review with you the difference between solutions and the actual answer. So there is 1 solution for x. What is the value of x? That's what you told me, Jared. The value is 4. But there's only 1 solution. So then, what if our equation is y equals x squared? Now, how many solutions are there for x? How many solutions do we have, Stephanie, for x? What can x be? If y equals 4, what would x equal? 2 or negative 2. So how many solutions do we have? 2 solutions. So the point here is not to confuse the value of something and how many possible solutions there are. Here we have 2 possible solutions. All right, one more math lesson before then we can work on our model of the atom. What does this graph look like? Any idea, Garrett? Your math teachers would be upset with you guys. Right? It's a circle. What is the value of the radius? 2. So this number here, the square root of that number gives you the radius. This is a 2-dimensional graph. It depends on only 2 variables, x and y. Now the atom is not a 2-dimensional thing. The atom is in 3 dimensions, x, y, and z. So when we are dealing with our last model of the atom, we are going to have to deal in 3 dimensions. The x dimension, the y dimension, and the z dimension. So we will be drawing in 3 dimensions, and you're going to get practice doing that. So, this equation, in 3 dimensions. You know what the shape is? Spherical. So we first draw our axes. So if it goes below the plane, we go dot, 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 dot. We come out behind the plane, dot, 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 dot. And there you go, dot, 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 dot. So first we draw our axes. when we draw in 3 dimensions, how do you draw a 3-dimensional sphere? Oh, I do have an apple. Even better. Okay, so how do you draw a 3-dimensional sphere on a 2-dimensional piece of paper? Well, what you do is you draw a circle. So that's the first thing you do, is you draw yourself a circle. And then you have to give it perspective. Okay? So what you do is you chop out a section of your sphere, just like you'd cut out a section of an apple. So you cut out a section of that to try to give yourself perspective. So I go like this, and then I shade the skin. And my radius is 2. So I've drawn a sphere of 2. So how many variables does this graph depend on? 3. X, Y, and Z. So like I said, to actually do the Schrodinger model of the atom, you need to know calculus. We don't know calculus. So what I'm going to try to do is give you kind of a descriptive picture of it by giving you an analogy here. Okay? Suppose I'm driving a car and I slam on the brakes. And I want to calculate how long it takes for my car to stop moving. So what are some things I would have to know in order to figure out how long it takes for my car to stop moving? What are some variables I would have to take into account?
How fast the car is?
So the speed. What are other variables you'd have to take into account? Yep, Rachel?
Friction or traction,
The friction of the
snow in the wheel.
snow in the wheels. So I'm driving fast, I slam on the brakes. I'm going to have to know how fast I'm going, friction of the road, mass of the car,
Gravity.
gravity, perhaps if I'm going downhill. And I'm sure there's some other ones we could come up with. We could maybe think about wind speed. Some other ones. So this is a pretty difficult problem to solve because we're going to have to take into account friction, the mass of the car, the speed of the car, the gravity, maybe even the wind. So when we have difficult problems to solve, we do things like this. We pretend that values are 0. We pretend that the car has no mass. We pretend that there is no friction. We pretend that gravity is not operating. And so then the time it takes for a car to stop will only depend on what? The speed. Now, that's not realistic, but it makes the math simpler. And we do that a lot in science. We say, okay, when you get to physics, you do this all the time. How long will it take a car to stop on a frictionless surface? How long will it take, or how much energy do you need to stop a parachuter, assuming there's no wind? Okay, so you always do these things to make your math easier. Okay. Now, the position of the electron, where the electron is located, depends on 4 things. these four variables, not speed, friction, mass, and gravity, but they depend on wave, angular momentum, magnetic field, and spin. And these four properties come from the properties of particles and waves. The electron's a particle, and it's a wave. So it's going to have properties of both. So the first property, the first variable, is called the wave value. The variable for the wave value is n. And what is the wave value? Waves must come in whole numbers. So, if you're going to describe the electron, you need to take into account that it's a wave. And what do waves do? Waves come in whole numbers. So if you go back to page 4 and 5 in our notes, we drew this. That's the first fundamental wave. That's the second fundamental wave. So if the electron is a wave, the waves must come in whole numbers. Can't have part of wave. So here is a wave property of the electron. Variable n. Now here's a particle property of the electron. If it has mass, it has momentum. Now we know how to calculate linear momentum, P equals mv. Mass, velocity, the electron has mass, the electron has velocity. You don't know how to calculate angular momentum. We'll save that for next year in physics. Okay, but there are equations for that. So all we're going to do is describe it. The variable is L. Angular momentum is when you are traveling in a circle, which the electron does, right? The third variable we have to take into account is, and here's the variable, the letter m with a subscript L. M subscript L, also known as m sub L. When an electron moves, it creates a magnetic field. Anything that's got a charge, when it moves, creates a magnetic field. And so, a moving charged particle creates a magnetic field. And next year, again, I know it's kind of exciting, but you have to wait till next year, Sam. There are a whole bunch of sets of equations that describe magnetic fields. We know that the magnetic field originates at the poles, and the strength of the magnetic field is the strongest at the poles. And so we can draw what's called field lines. Field lines tell you where the strength is the greatest. The more lines, the greater the strength. So a magnet is very strong there and very strong there. It's not so strong right there. Okay? Those are called the Maxwell Equations. Next year we'll have a lot of fun playing with those, explaining the strength of magnets, what happens to the force the farther you get away. You can be right here and you won't feel the magnet at all, but if you go over there, you'll feel the force of the magnet. So there's a nice description in physics next year. But also, you don't know the equations for those either. So you don't know that, you don't know that, you don't know that. And the last one, spin. variable m subscript s. And this is called the spin. The electron appears to be rotating on an axis. Now, why do I say appears? Because you can't see the electron. But when they make their measurements tell them that they think it's rotating. But they can't prove it for sure because you can't find the electron. So it appears that it's rotating, so that's the fourth and final variable. The electron can rotate clockwise or counterclockwise. This is more like a particle property. The Earth can rotate two directions, clockwise or counterclockwise. So these are the four variables that affect the location of the electron. Just like these are the four variables that affect the time it takes your car to stop. Any questions so far? Okay, so how did we solve this problem up here? We pretended there was no friction, no mass, and no gravity. How are we going to solve this problem right here? Same way. We're going to make it simple. We're going to assume these variables are zero, except for the first one. So we are going to solve, in quotations, Schrodinger equation. And the way you would write it is the way it's written on your paper there. We're going to start with psi equals n equal 1, L is 0, m sub L 0. N equal to 1 is the first fundamental wave. So we start off assuming that all those other variables are 0. The only variable that's not 0 is n. And here's the equation. Okay? We graph this, right, Lauren? What did we get? Circle. Okay? All we did was take an equation and we graphed it. We got a circle. Same principle. Here's my equation. There's my equation. Now let's graph it. To graph it, you will need to know calculus. And you will need to know, what do they call that, radians? Unit circle? Okay, which I'm guessing you're pretty hazy on the unit circle too. So obviously we're not going to actually do the math. I'm going to graph it for you, but the idea here, Quinn, is you've got an equation and you graph it. That's it. Okay? So here's what the graph looks like. So this is what you guys are going to draw. That's the graph.
Is that X and Y axis?
Yep, x and y axis. Y, x. And then we square this graph. Just like we did in that earlier lesson, we're going to square it. And this is what happens when you square it. The graph then looks like this. That's the nucleus. This is the distance from nucleus. So our x-axis is telling us how far away from the nucleus we are. And the y-axis is telling me the probability of finding the electron. So like I said, the quantum mechanical model does not deal in certainty. It deals in probability. So if I want to know where this little yellow ball is, what's the probability that it's in my left hand? What's the probability that it's in my right hand? 50%. Okay? We don't know where it is. All we can do is assign a probability to a location. 50% chance in my left hand, 50% chance in my right hand. So, same thing here. We are assigning a probability to a location. If I go 0.529 angstroms away, so I'm going to go 0.529 angstroms away from the nucleus. The probability of finding the electron there is 59%. This is the Schrodinger model. We are assigning a probability to every place in space. So 0.529 angstroms away, 0.529 angstroms away, the probability of finding an electron is 59%. What happens to the probability if I go closer to the nucleus? What happens to my probability? Does it go up or down? Down. What happens if I'm in the nucleus? What's my probability of finding the electron in the nucleus? 0. Okay? If I start to go farther away, what happens to my probability? It's less. And eventually, out at infinity, my probability is 0. So there are two places of 0 probability. The nucleus and at infinity. And that sort of matches up with my wave. Where is there 0 amplitude? At the beginning and at the end. Where is there 0 probability? At the beginning, in the nucleus, and at the end, at infinity. Monkey, you got a question?
If they don't know where the electron is, how can they assign the probability where it would be?
Based on what they know about the properties of electrons. They know electrons are waves. They know electrons have mass. They know electrons are orbiting, so they have angular momentum. They know they have a charge, so it creates a magnetic field. And there are all these equations that control those factors, okay? So there are laws that explain how magnetic fields are created. There are laws that explain how things orbit. And there are laws that explain waves. So they take all those laws together, and that's why you have such a complex equation, and you graph it, and it tells you where it can be or where it can't be. But they don't know for sure, because it's all based on probability. So if you thought it was already bad, it gets worse. This equation is in 2 dimensions. Okay? The atom is in 3. So we have to take this graph here, Quinn, and we have to put it into 3 dimensions. You ready? Doesn't matter, we're doing it anyway. All right, so let's draw our 3-dimensional axes. what does this graph look like in 3 dimensions? It's actually a sphere. So we have to draw ourselves a sphere. And to draw a sphere in 2 dimensions, you draw a circle. You chop out a section of it. You shave the skin. And what is the radius of my sphere? The radius of my sphere is 0.529 angstroms. That's the greatest probability of finding the electron. So to draw a little perspective in, you draw in a ray, and that's my radius, 0.529 angstroms. And what is the probability of finding an electron 0.529 angstroms away? 59%. So it doesn't matter if I'm going that direction or that direction or that direction or that direction or that direction. If I'm 0.259 angstroms away, the probability is 59%. Yeah, Garrett, you had a question.
How is it a sphere?
Well, it's not a perfect sphere. It's what we call a fuzzy sphere. And so really, I'm going to redraw it for you over on the chalkboard, because the chalkboard, I can add better depth and shading. Yep.
Is there a like sign thing for probability? Like a symbol?
For probability, psi squared is probability.